Greetings viewers, today we'll do Cambridge A-Level Further Maths Syllabus Code 9231. This is Further Pure Paper 2, Variant 4 from the May June 2025 series. We'll attempt question 4 in this video. The previous questions have been uploaded into the same playlist. So it's giving us a curve with some parametric equations. First of all, they want us to show that the only root of x in terms of t is 1. So if you remember from polynomials, I forgot what was the theorem already. The remainder theorem, right? If 1 is the root, so we divide by t minus 1. So t minus 1 is a root. Obviously, you can use your synthetic division or whatever method that you have learned, but I will use the long division, this method. Once you completed the division, this will yield that x of t is the root. I mean, first of all, the root that they're giving you, and then also the root that you found, which is t squared plus 1. So obviously, you know that t squared minus 1, no real roots. So as long as you prove this, then you should be fine. As long as yeah, this one only real root is here. Okay, so that's question A. Now we want to show the derivative, the first derivative, dy dx, is this expression. So obviously it's giving us a parametric equation here. We only can differentiate with respect to t, but then we are using the chain rule, that dy dx will be dy and dx. And then in between we'll use the dt as a chain rule to connect or to relate the two differentials. So first we find dy dt. Okay, y of t is t e to the power of t. So therefore, we need to use the product rule here because t multiplied by e to the t, that is a product of two functions. So dy dt. Alright, first I'll leave the t, I'll differentiate the e of t. The e of t differentiate is the same thing. Then I will differentiate the t, which gives 1, and then e of t stays the same. So we can even factorize this to become t plus 1 e to the t. Right, so I factorize it like that because the common factor is e to the t. Okay, so that's dy dt and dx dt. Okay, dx dt is a polynomial, so it's pretty straightforward to do. So we just minus 1 from the power and multiply it down. And the plus 1, the minus 1 is a constant, so once you differentiate, that just goes to 0. And okay, finally, we'll use this relation, the chain rule, dy dx, dy dt, we have that t plus 1 e to the t, and then dt dx. Okay, dt dx, that's the reciprocal of dx dt. So we rewrite the expression for dx dt and the reciprocal. So simplifying or become more explicit, we can present it in the exact form that they want, just like that. Okay, so that and shown. Okay, so that's part B. Part C, they want us to find the Maclaurin series for y up to and including the term x squared. Okay, if you somehow forget the Maclaurin series, it's given in the formula sheet. Okay, so we're using the general expression of the Maclaurin series here. So fx is, first of all, is the original function evaluated at 0, then x multiplied the derivative evaluated at 0, then x squared over 2 factorial multiplied by the second derivative evaluated at 0. So let's just just write it out first. F of 0, f prime of 0, then x squared over 2 factorial, and the second derivative, okay. So obviously we have we don't even have the original function yet, right? Okay, so let's find the original function first. Okay, first we want to find f of 0, right? But we are only given x of t and y of t. So we want, actually what we want is our in the Maclaurin series here, actually what we have is y is the dependent variable on x. So x is the independent variable in this case, and you want actually y of 0. We want the case where x is 0. So obviously we've used in part A, when x is 0, the only real value for that to be true is when t is 1. Okay, so maybe already like this better. Y when x is 0 is y when t is 1. Okay, so because we want, I mean, as again using the Maclaurin series, we want to evaluate the dependent variable when the independent variable is 0. But in this case, our independent variable is dependent on another variable, parametric function of t. So when t is 1, only then our independent variable will be 0, right? As we proved in part A. So we'll use that result and substitute that into our the y of t, right? So we just get the e, okay, as a constant. So y of 0, y when x is 0, that will be e. Now we move on to um, f prime of 0. Sorry, y prime when x is 0. So again, we use the parametric relation. So y prime when t is 1. Okay, and I'll just copy down this. I will use this relation. Again, we get just the e. If you have the first term and the second term of the Maclaurin series already, now we want to find the second derivative, or f double prime. But that we don't know, or we haven't found, because we only found up to the first derivative for now. Let me just write that. Okay, so that's our expression for dy dx. To find the second derivative, okay, d squared y dx squared, using the chain rule, we need to do this. First, our expression for the first derivative is in terms of t. So we only can take the derivative of that in terms of t. dy dx. Then we need to use the chain rule again to multiply by, we want it to get rid of the dt, so we multiply by dt dx. So eventually we'll get the second derivative. So this is the chain rule that we are applying again. So first, let's take the derivative in terms of t of the dy dx. And this, we need to use the quotient rule. Okay, quotient rule, we need to use all three rules: the quotient rule, product rule, and chain rule here. So first, we take the bottom to the top, take the denominator to the numerator, just leave it, we don't differentiate it first. Then we differentiate the top function, which we need to use the product rule here. So I'll leave the first part and differentiate the e power t, which is get e power t. Then I'll differentiate the t plus 1, you just get 1 plus e power t. Okay, so that's the first part of the quotient rule. Then I'll minus the derivative of the bottom, so 6t minus 2. And then I'll leave the top, t plus 1 e to the t. Everything divided by the bottom squared. Okay, we square it like that. So that's just the first derivative differentiated with t. So now we want to get the second derivative, d squared y dx squared. We take this and we multiply by dt dx. dt dx, of course, is the reciprocal of the quadratic expression. So it's the same thing as the denominator here. So we're just going to add 1 to the power to the denominator. in between, I've also factored out the e to the power of t in the this term so that it becomes t plus 2. Okay, that's the only other thing that I've did here. But you don't need to simplify this any further because we know that we want to evaluate this term when x equals to 0. So we evaluate the second derivative when x equals to 0, which is the same as saying as we evaluate the second derivative when t equals to 1. Because again, our expression is in terms of t, so we only can work with that. So be careful when you substitute the values in. That's the mistake, or most of the mistake comes from the derivatives and also the substitution of values. So just be careful here and you should be fine. You should be able to find that your second derivative evaluated when x equals to 0 is negative e over 4, and therefore to just substitute back into the um, Maclaurin series, so we get the approximation y of x. So the first term we just leave as is, so it's just e. Then second term you have e multiplied by x. The third term we have negative e to the 4. I mean e divided by 4 divided again by 2 prime of 2 factorial, sorry, then multiplied by x squared. Then you have plus dot dot dot. So simplification is e over 8 x squared. So yep, that's the Maclaurin series. Most common mistake the students that will make is when they forget to apply the chain rule here, or some careless mistakes when they do the derivative or when they substitute the values, right? So just be careful when you're doing that, and you should be able to get this expression. And obviously Maclaurin series, there's a many application in real life when you want to approximate some function uh, so that I mean you don't, so that the computer or the computational cost is not that high, right? So you don't need to go for the or how many, depending on how accurate that you want the answer, you don't need to expand so many terms of the Maclaurin series. So you can just approximate maybe with 2 or 3 terms is maybe it's accurate enough for that accurate application. But if you want to go for larger accuracy, if you don't care about the computational cost, you can even expand to 10 like a lot of terms. So that is some of the application of the Maclaurin series. So yeah, thank you for watching.